Hello students, welcome you all. In NMR spectroscopy, that is nuclear magnetic resonance spectroscopy, today I will give you the introduction, and in introduction I will give you the brief idea about nuclear spin and nuclear spin states. And in my next lecture I will give you the detail of the basic principle of NMR spectroscopy. But before going to that, in one line, what this NMR spectroscopy is, by this title, that is nuclear magnetic resonance spectroscopy. So this technique, it deals with the nuclei. It deals with the nuclei of an atom. What we read in UV visible spectroscopy, the electron of an atom that absorbs the UV visible radiation. Here in NMR spectroscopy, nuclei of an atom absorbs the radio frequency. In presence of external magnetic field, then resonance takes place and we get the NMR signal. Okay, so in one line what you may understand that this nuclei of an atom absorbs the electromagnetic radiation. Which type of electromagnetic radiation? Which falls in radio frequency region. And so what radio frequency region? Which radio frequency region? Usually the radio frequency region approximate range is from 4 megahertz to 900 megahertz. This is the approximate range. But the spectrophotometer usually comes in the market. They have this frequency range around from 300 megahertz to 800 megahertz. Higher is this frequency, higher is the frequency of a spectrophotometer, better will be the result. Better we will get the resolution will be, the better is the resolution. So nuclei of an atom absorbs the electromagnetic radiation. Which type of electromagnetic radiation? Radio frequency. Electromagnetic radiation is absorbed, and this absorption takes place in presence of external magnetic field. To get resonance. Resonance takes place when the absorption occurs. So after absorption, resonance takes place to give NMR signals. Then we will get the NMR signals. Okay, so what type of nuclei that can be studied in NMR spectroscopy? So usually the different nuclei which can be studied like proton, which is called as, this is called as the proton NMR spectroscopy. When the nuclei is proton, then it is called as the proton NMR spectroscopy. When nuclei is this isotope of this carbon, that is carbon 13, then it is called as the 13 carbon NMR spectroscopy. In the same way, this fluorine can also absorb the and that can also absorb the NMR radio frequency. So it is called as the fluorine NMR spectroscopy. Like phosphorus can also absorb phosphorus 31. So phosphorus NMR spectroscopy, and so on. The different NMR spectroscopy we can study. Okay, so these are the different nuclei which can absorb the radio frequency. Okay, now so after absorption, then we get the NMR signal. So how many NMR signals that we can get? So number of this NMR signal, that is equal to the number of different type of nuclei. Suppose in a molecule there will be many protons. There are many protons, and each proton will have the different environment. If environment is different, then their proton are said to be different, and that proton are said to be distinct proton. And in the same way, if many carbon-13 are there, and if this carbon-13 atom has a different environment, then they are said to be the different carbon-13 or distinct carbon-13. So depending upon the different environment of nuclei, we will have a NMR signal. So number of NMR signals is equal to number of distinct type of or different type of nuclei. So if any molecule, if we have three type of different proton, that is having the different environment, then we will have the 3 NMR signal. If in any molecule, if we have 20 type of different proton, that is 20 type of proton having the different environment, then we will have 20 NMR signals, and so on. Okay, so what information will we get in a NMR spectroscopy? We get the different types of proton can be studied, different types of carbon-13 can be studied in a molecule, different types of fluorine in a molecule can be studied, different type of phosphorus in a molecule can be studied by the NMR spectroscopic technique, and so on. Okay, so this which kind of proton that gives the NMR signal? Here I have written this 1H. So whether this deuterium can give the NMR signal, whether tritium can give the NMR signal, whether oxygen molecule can give the NMR signal, so that we have studied, and that depends upon the nuclear magnetic quantum number. So before coming to the nuclear magnetic quantum number, we should know about the nuclear spin. So let us come to the nuclear spin. So we know that the electron can spin around its own axis. All of you know that electron can spin around its own axis, and due to this spinning electron, they behaves like a tiny magnet. In the same way, the proton can also spin around its own axis. Like an electron, proton can also spin around its own axis, and it can also behave as a tiny magnet. And if it behaves as a tiny magnet, then it will have certain direction of magnetic field. Okay, so what we can write, like an electron, the protons can also proton can also spin. Okay, proton can also spin, and due to which they behave as tiny magnet. And as they behave as tiny magnet, then they will have certain magnetic field, and thus have a particular direction of magnetic field. Direction of magnetic field. And we can know about the direction of this magnetic field also. Okay, So we can know about the direction of this magnetic field. So direction of magnetic field in a spinning proton. We can get the direction of magnetic field in a spinning proton. So, this direction that can be determined by right hand thumb rule. So this direction can be determined by right hand thumb rule. Right hand thumb rule. So what this right hand thumb rule says? So what this right hand thumb rule says, suppose if we have a proton, proton means, if we have a nuclei, and nuclei is having proton and neutron. Nuclei is having proton and neutron, and suppose if it is rotating in this direction, it is rotating like this. It is rotating like this. Means, suppose if I have a palm, then this palm, the rotation of this palm, it gives you the direction of the nuclei. So suppose I am rotating the palm like this. Then direction of rotation of my palm is the direction of rotation of this nuclei. As you can see, this is the direction of rotation of my palm. So this is the same is the direction of rotation of the nuclei. So if this is the direction of rotation of my palm, then the direction of this thumb will give you the direction of a magnetic field. So if the palm is rotating in this way, then the direction of magnetic field is upward. So in this case, this is the direction of magnetic field, which is going upward. So this is the direction of magnetic field. Okay, means this is the north, this will be the south. In the same way, suppose the nuclei is rotating in this direction. If this is rotating in this direction, means now if it is rotating in this direction, suppose this is rotating in this direction, okay, means what kind of rotation? This is our clockwise rotation. If it is clockwise rotation, then our direction of the thumb is downward. So this is the direction of thumb. This will give you the direction of magnetic field. So this is the north and this would be the south. Okay. So this is about the nuclei, and about the electron, the rule is just reverse. Rule is just reverse for the electron. So this is the rule for nuclei. So these are the nuclei of an atom. And for electron, suppose if this is the electron, if it is rotating in a anti-clockwise manner, and according to the right hand thumb rule, so the rule will be the reverse. So in this case, the direction of magnetic field, this would be the direction of magnetic field. This is north, this is south. And if it is rotating like this, and if it is rotating like this, electron, if it is rotating like this, then this would be the direction of magnetic field. So this is for electron, and this is for nuclei of an atom. This is for nuclei of an atom. Okay, so if you see, suppose we have a nucleus. We have a nucleus containing proton and neutron, and if it is rotating in a anti-clockwise manner, that is like this. This is a rotation of palm, which is the rotation of the nuclei. Then this thumb, that is the direction of our magnetic field. So this is the direction of magnetic field, that is, this is north and this would be south. And surrounding this nuclei, we have an electron. And suppose this is the electron, and this electron is rotating in this direction. Then In this case, the direction of magnetic field, this would be the direction of magnetic field. This is north, this would be south. And suppose the electron is rotating in this manner, in this clockwise manner, then in clockwise manner, this would be the direction of magnetic field. This is north and this is south. Okay, so if electron and protons are rotating and on its own axis, then they will have certain magnetic moment. So what would be the magnetic moment for the electron? So magnetic moment for the spinning electron, if you say magnetic, or what we should say, the momentum. So momentum of an spinning electron, momentum of spinning electron is given by the formula root over s plus 1 h upon 2 pi. H upon 2 pi, this is the momentum of a spinning electron, where s is the spin quantum number. S is the spin quantum number of an electron, and this is, we know that spin quantum number, this is plus minus half is the spin quantum number of an electron. Whereas if we have this proton, then what would be the momentum of spinning proton? So momentum of spinning proton this is equal to root over I plus 1 multiplied by h upon 2 pi. So this is the momentum of spinning proton, where here this I is the spin quantum number of the proton, s is the spin quantum number of electron, and here the value of I, it may be n by 2, where this n is equal to 1, 2, 3, 4 and so on, whole number. So n, I may have value either whole number 1, 2, 3, 4, 5 and so on, or it may have value 1 by 2, 3 by 2, 5 by 2 and so on. So this I is the nuclear spin quantum number, and the overall this nuclear spin quantum number of any nuclei, that should depend upon we are talking about the nuclei of an atom, and this nuclei of an atom have certain I value, and the I of this nuclei, that should depend upon the proton as well as neutron. That is number of proton and number of neutron. Like it means this proton and neutron, it is also having some quantum number. They are also spinning. Proton and neutrons are also spinning, and they will also have certain quantum number. But overall, the value of this I for a nuclei, that depends upon the value of the P and N, and which so total value of this I, that depends upon the number of proton and neutron, how they are spinning and so on. So let us see about this nuclear spin quantum number. So this nuclear spin quantum number I, nuclear spin quantum number, that is this I. This depends upon the number of protons and number of neutrons. number of neutrons. Okay. So if any nuclei is having some value of I, then only that nuclei is said to be NMR active nuclei. Suppose if any nuclei is having I is equal to 0, then that nuclei is NMR inactive nuclei. So this is one of the selection rules. So what this selection rule tells, selection rule for this NMR spectroscopy. So selection rule for this NMR spectroscopy is that if I is not equal to 0, then only the nuclei is NMR active. Then nuclei is said to be NMR active nuclei. Okay, and if this I is equal to 0, then such nuclei is NMR inactive. So what I told you, the value of this I, this depends upon the number of proton and number of neutron. So let us see how this value depends upon this. Now suppose if we have different protons, different neutrons. So suppose this is for number of proton, this is for number of neutron. Okay, and here we have the value I, and now let us see some examples which are either NMR active or not. NMR, either it is active or it is inactive. Let us see. Depending upon this, whether the nuclei are NMR active or inactive, that depends upon the number of proton and neutron, and the total value of this I, that depends upon the number of proton and number of neutron. Now suppose the number of proton in any molecule is even, or atom is even, and this is also even. Any atom, number of proton as well as number of neutron are even, both are even. Then in such case, the I, then I that will be equal to 0. If number of proton and number of neutron are even, then I is said to be 0, and such nuclei are NMR inactive. Such nuclei are NMR inactive. For example, if you will see, then for example, this carbon 12. In carbon 12, number of proton is equal to number of electron. 6 is the number of proton as well as number of electron. And if 6 is the number of proton, then 12 minus 6 is the number of neutron. So 6 and 6, proton as well as neutron, both are even. So this nuclei is NMR inactive nuclei. In the same way, if we have suppose oxygen 16, this is also NMR inactive nuclei. Okay, and so these two are NMR inactive, and suppose if we have if we have even case, suppose if we have fluorine, suppose these two. Now suppose the number of proton is even and number of neutron is odd. Or other case, if this is odd and this is even. Okay, one is odd and another is even, or one is even and another is odd, then in such case the I value is the fractional. For example, it may be 1 by 2, it may be 3 by 2, it may be 5 by 2, and so on. So some of the examples. So for such, where the I value is not equal to 0, then such nuclei are said to be NMR active nuclei. And for example, it may be, for example, proton. Number of proton is 1. Number of neutron is 1 minus 1, that is 0, which is even. And then if we have carbon 13, number of proton is 6, number of neutron is 7. In the same way, if we have suppose neutron, or suppose if we have fluorine 9 and 19, number of proton is 9, number of neutron is 10. If we have suppose here, if we have chlorine 17 and this is 35, okay, chlorine 17 and 35, this is our odd, this is odd, number of proton 17 is odd, and number of neutron is coming out to be 18, which is even. So one is odd and another is even, and so on. So these nuclei, these in the same way phosphorus, this phosphorus 15 and 31. Okay, so these are the NMR active nuclei where one is even and another is odd, and so on. Now, so some of the protons, some of the examples where both are, suppose proton is odd as well as the neutron is also odd. Then in such case, the I value that would be the whole number, and it is 1, either 2, 3, and so on. And such nuclei are also NMR active nuclei. They are also NMR active nuclei. And for example, it may be suppose deuterium, it may be deuterium, or it may be suppose nitrogen, nitrogen 15, okay, nitrogen 14. So here this is odd, proton is odd, 14 minus 7, the neutron is also odd. So these nuclei are some NMR active nuclei and some are NMR inactive nuclei. Now, so what I told you, the nuclei are spinning like that of electron. All nuclei are spinning like that of electron, and they spin in a random direction. In a random direction they are spinning. But once we apply a magnetic field, then in that case the orientation of nuclei are fixed, or we can say they have a fixed direction of spinning. So in presence of external magnetic field, the direction of magnetic field is fixed. They have the certain fixed orientation. So suppose if we have no magnetic field, then some of the nuclei, the direction of nuclei would be, some would be like this, like this. So they are the different direction, random. They are random one. Okay, so in absence of magnetic field, direction is random. And in presence of magnetic field, if we apply an external magnetic field, suppose an external magnetic field is applied, suppose B0 is the external magnetic field, then the nuclei will have certain fixed direction. Nuclei is having some fixed direction. Okay, so this is the direction, or it may have this direction. So in presence of external magnetic field, the orientation of nuclei in space is fixed. So this is in external magnetic field. In external magnetic field, there is a fixed direction of magnetic field. There is a fixed direction of nuclei. Direction is fixed. Okay, so we can have a different orientation. Okay, we can have a different orientation of nuclei, and we will see the possible orientation of nuclei in space, or we may also call it the spin states of the nuclei, energy states of the nuclei, or we say that the nuclear spin states. So now I will give you the idea about the nuclear spin states. So for a particular value of I, for particular value of I, number of nuclear spin state or we can say number of energy states this is equal to 2I plus 1. Okay, suppose if I is equal to 0, then number of energy state will be 1. If I is equal to half, number of energy state that would be 2. If I is equal to suppose 1, number of energy state that would be 3. And it will have, so for particular value of I, a certain fixed number of states are there, and that specific number, it lies from suppose from plus I to minus I, like this. So suppose if I is equal to your 3, then what would be the energy state? For if I is equal to 3 means suppose I is equal to 3 by 2. If I is equal to 3 by 2, the number of energy states that would be equal to 3 by 2 means 4. Total number of energy states would be 4. So 4 plus 4 minus 4 and plus 4 plus 3 and like this. So different energy states would be there. Okay. Now, so let us see the different possible orientations of spin. Now suppose this is the value of I, then value of 2I plus 1 and orientation, possible orientation of spin, possible orientation of spin, and then energy states. Or we can say spin state or nuclear spin state. Now suppose if I is equal to 0, then total number of, that is the, it is also called as the spin multiplicity also. So this 2I plus 1, this is equal to 1. And the possible orientation, in this case suppose this would be the possible orientation. This is the only possible orientation. This is north and this is south, like this. So we may show the energy state like this. We may show the energy state. So this is the only possible orientation. Okay. So for I is equal to 0. Now suppose for I is equal to half, 2I plus 1 value, that would be equal to, that is equal to 2. And the possible orientation, we may say the possible one of this orientation. This is one of the orientation, north, south, and this would be the on another orientation. This is north and this would be the south. So means that direction of this magnetic field is in this direction. It means this is the direction of magnetic field. this is the direction of magnetic field. It means the nuclei, the direction of nuclei is like this. So it is rotating like this. So I may give the direction of rotation of nuclei like this. Now if the direction of magnetic field is this is the thumb is the direction of magnetic field, then our nuclei is rotating in this direction like this. So I may write this is the direction of rotation of nuclei, and this is the direction of rotation, this is the direction of magnetic field. So here we have the two possible orientation. So two possible orientation, it means we may write it like this. Two possible orientation means one would be plus half, another would be minus half. So plus half and minus half. This plus half, this is also called as the alpha state, and this minus half, this is also called as the beta state. Alpha state and beta state. Okay, now in the same way, suppose if I is equal to 1, then 2i plus 1 value, this is equal to 3. So what are the three possible orientations of a spin? Three possible orientation. Suppose this would be the one possible orientation, and other orientation, this would be the another orientation, north, south, and this is north, this is south. So these are the three possible orientation. Okay, so one magnetic field direction is up, another is on the right side, another is on the left side. Now energy states, how we can show the energy states? We may show the energy state. This is one of the energy state, second one, and this is third one. Okay, so it means plus 1, minus 1 and 0. These are the three energy states that we may show. In the same way, suppose 3 by 2, I is equal to 3 by 2, then number of this 2i plus 1 value, nuclear spin states, that would be, how many spin states would be there? 3 by 2 means 4 spin states would be there, and we may show the four possible orientation. Suppose this is one of the possible orientation. This is north, this is south. Okay, so means direction is like this. This is the direction of thumb, which is the direction of magnetic field, and the direction of rotation of nuclei would be like this. So this is the direction of rotation of nuclei, and I may show like this, the direction of rotation of nuclei. Here, if suppose another possible orientation, this is another possible orientation, this is the another possible orientation, this is north, this is south. So as you can see, this is my direction of rotation of magnetic field. This is the magnetic field. The thumb is the direction of magnetic field. If thumb is the direction of magnetic field, it means the nuclei is rotating in the direction of my palm. So our direction of my palm is like this. Direction of palm is like this. So this is the direction of palm. If this is the direction of rotation of this palm is rotating this way. So this is the direction of rotation of my palm. Next, same to this may be the two direction. These may be the two direction. So another direction. This is one of the direction. And another direction would be, this would be the another direction, north, south. So these are the four possible orientation of a spin, and the energy states that we may show the energy state. Four energy states is 1, 2, 3, 4. Means 3 by 2 plus 3 by 2 plus 1 by 2 minus 1 by 2 and plus 3 by 2. Okay, so that we may show. So this is 3 by 2 plus 3 by 2 minus 3 by 2. 3 by 2 minus 1 is 1 by 2, and minus 3 by 2 plus 1 is -1 by 2, and like this. In a same way, suppose if this is 2, then direction, how many spin states? 5 spin states, and we may show the 5 spin states like this. This is one of the spin state, north, south, and other 4 spin states, these will be the other 4 spin states that I may show like this. This is the one, this is the another one, north, south, this is the another one, and this is the next one. North, south, and direction of rotation of nuclei would be like this. And we may show the 5 energy states. So how means +2, +1, 0, -1, -2. These are the 5 energy states or 5 spin states, and so on. So this is about the nuclear spin and nuclear spin states. Now in my next lecture I will give you the detail of the basic principle of NMR spectroscopy, where I will discuss the precession of nuclei, or we can say the precessional frequency or Larmor frequency, that I will discuss. Okay, thank you.